of division of polynomials. Here's an example. Let's say 3x squared minus 4x minus 3 divided by x. You see I have a polynomial at the top, but I have only one term in the denominator. The only thing I can do is just separate the fraction into 3 fractions. I cannot do this if the denominator has more than one term. Do not try. It's not allowed. So in this case, I'll simplify this as 3. I'll simplify 3x. I'll simplify this as 4, and then there is nothing I can do to this. And you can say, what did you accomplish? Well, this is the only way. I simplify 3x squared over by x, x divided by x. I'll simplify here by x, and I get 4, and this is it. The second situation is kind of twofold. Why? It's because we can have a polynomial divided by a binomial. But if the binomial is x minus a, which means degree 1, extremely important, degree 1. Degree 1. So what could this denominator be? Well, let's say x plus 1, or x minus 3, or x plus 7, or x minus 4, etc. In this situation, we have two possibilities. We can use what is called long division, or we can use synthetic division. Okay, so let's refresh our memory on the long division with an example. So let's choose. Feel free to choose if you'd like. These problems are on page. We do not cover section 3.4. They are on page 392. And feel free to choose from 17 through 26.
24.
24 is good. Okay, so let's look at 24, in which we have x to the 5th plus 4 x to the 4th minus 3x squared and plus 2x and minus, plus 3 divided by x minus 3. So let's illustrate with the long division first. And there are few settings that we have to take care of before we do anything. So number one, that I have to make sure that number one happens, which is descending order. If these two polynomials are not in descending order, I have to put them in descending order. It's a must. Number two, I'm going to have to ask myself if there is a missing term from the top. Missing term from the numerator. And the obvious question is, how will I know? Well, very easy, I know. Can anyone give us the degree of this polynomial? Indeed. It must have 6 terms. 1 with degree 5, 1 with degree 4, 1 with degree 3, 1 with degree 2, and 1 with degree 0. It has 5 terms. 1, 2, 3, 4, 5. Okay? So there is no missing term.
38, right?
Oh, there is an x. Oh, yes, right. I'm sorry. X to the 3rd is missing. Sorry. Degree 5, 6 terms. I have only 5. So 1 term is missing. Sorry. It's Monday.
Hey, at least I'm paying attention.
No excuses. No excuses. I'm sorry. My apologies. So 1, 2, 3, 4, 5, 6. But this one is missing. Because it's missing, I will have to leave some space for it. Empty space. X, you can put 0 if you like. Plus 4x to the 4th. The 3rd one is missing. minus 3x squared plus 2x and plus 3. And I divide by x minus 3. The same with division with numbers, numerical division. However, this is slightly different because of x. Ready? X times what is x to the fifth? X to the fourth. We have to go back and distribute to both terms. We have to write under like terms and change the sign to the opposite sign. How much is x to the fourth times x? But I have to subtract. Because I have to subtract. X to the fourth times negative 3 is negative 3x to the fourth, but I have to subtract. Yes?
Oh, no. Oh, I'm just, yeah, no.
So 7x to the fourth. I should be bringing down this one that is missing. So now the next question is, and at the top we do not lie, quote unquote, you know what I mean. X times what is 7x to the fourth. So I do not lie. I have to see, I have to write the correct symbol or sign. What sign?
Plus.
Yes. Plus what? 7x cubed. If this is x to the fourth, the next one has to be the next in line, most probably. I go now and distribute to these two terms. 7x cubed times 7 is 7x to the fourth, but I have to subtract. 7x to the third times negative 3 is negative 21x cubed, but I have to subtract. See, I could have not written it under anything because it's under the missing term. These two go away. Copy 21x cubed and bring down the next in line.
I do have one question.
Sure.
So we are, it's division. So it's the x, we're doing the x first. So how many?
X times what is x to the fifth must be x to the fourth. X to the fourth times this is negative x. It's x to the fourth, but I have to subtract. X to the fifth, but I have to subtract. X to the fourth times negative 3 is negative 3x to the fourth, but I have to subtract. You understand why we subtract, correct? Okay, let's take a look. So when I divide, I know we don't do this anymore, but when I divide, let's say 3942 by 23. 23 goes into 39 once. 1 times 23 is 23. But if I write 23, then I will be adding. So that's why I have to subtract.
Okay.
And that's why I have to change the sign every time I write underneath.
Okay.
The same idea. But of course, this looks differently because it has x in it.
Okay.
That's why we always change the sign before we write underneath. Is that better? Is it clear? Are you caught up here till here?
Mm-hmm.
Okay, so we bring down negative 3x squared. X times y is 21x cubed. If this is degree 4 and this is degree 3, do not turn around. You have to continue going down, right? So this is positive 21x squared. 21x squared times x is 21x cubed, but I have to subtract. 21x squared times negative 3 is negative 63, but I have to subtract. And then 60x squared, and I bring down the next in line. Who chose this problem? No, I'm kidding.
Right.
X times what is 60x squared? And the sign. We do not lie at the top. You know what I mean? I'm just trying to be funny to trigger your memory. So 60x times x is 60x squared, but now I have to subtract. 60x times negative 3 is negative 180, and I have to subtract positive 180x. Go away, 182x. Final question. X times what is 182x? Of course, I have to bring down 3. And the answer is positive 182. So negative 182x and this is minus but plus. 4 and 2, 5. What do I box in? Box in 549. Now the question is, I have to ask you how to write the answer. So if I divide, let's say 10 by 3, I can write 3 and 1/3. But this is not acceptable for polynomials. For polynomials, I have to write 3 as the quotient plus 1 over the remainder. So this is the quotient. This is the remainder. This is the divisor. So can anyone give us the final answer of this division? I'm going to write it from the beginning. So the division was x to the 4th plus 7x. I'm copying something else. X to the 5th plus 4x to the 4th minus 3x squared plus 2x plus 3 divided by x minus 3. And I have to write the quotient. So here's the quotient right here. X to the 4th plus 7x cubed plus 21x squared plus 60x plus 182. And the remainder is 549 plus 549 divided by x minus 3. So this was the long division, and let's work on the same problem using synthetic division.
So that's how you would answer the question.
Yes.
Okay.
So now you can say, wait a minute, I don't trust you. And then I'll say, well, we're going to use a second method right now. But you can still say, show me that this is correct. Forget about the second method. You can make an error in both and get the same answer. How you show me this, that it's correct? Here's how I show you that this is correct. Is the way I show you that 10 divided by 3 equals 3 plus 1/3. I'll say this. 3 times 3 plus 1 is 10. X minus 3 times this plus 549 must be this. 3 times 3 plus 1 must be this. This times this plus this must be that. If it isn't, then this is wrong. So I'm going to multiply. X to the 4th plus 7x cubed plus 21x squared plus 60x plus 182 multiplied by x minus 3. And then I'm going to add 549. If I do not get this, then my division is wrong. 3 times 3 plus 1 has to be 10. This times this plus 549 has to give us this. If it doesn't, we have to start from scratch. So let's do that. X times x to the 4th, x to the 5th, plus 7x to the 4th, plus 21x cubed, plus 60x squared, plus 182x, minus 3 times this, 3x to the 4th, minus 21x cubed, minus 63x squared, minus 180x, minus 546 plus 549. Let's see. X to the 5th, yes. 7x to the 4th minus 3x to the 4th, yes. 21x cubed minus 21x cubed, yes. 60x squared minus 63x squared, yes. 182 minus 180x, yes. And negative 546 plus 549, 3. So it must be correct. Now let's illustrate with synthetic division. So the synthetic division is applicable in this case only because the denominator is, where is it? Right here. Because the denominator is x minus a number. So I compare x minus 3 to x minus a. Can anyone give us a? We've done this before when we graphed polynomial functions. We've done this before when we looked at the circle. Can anyone identify, compare these two and identify a? A is 3. What if I have what if I have x plus 5? How much will A be? Negative 5. This is the number that goes in this box. So I compare x minus A to x minus 3. I identify that A is 3, and it goes in the box. In the next step, I copy the coefficients in order, but this time I have to put a 0. What is the coefficient of x to the 5th? 1. What is the coefficient of x to the 4th? What is the coefficient of x cubed? 0. What is the coefficient of x squared? Negative 3. What is the coefficient of x? 2. What is the free term? 3. Exactly the same coefficients we basically used for the long division. 1, 4, 0, negative 3, 2, 3. 1, 4, 0, negative 3, 2, 3. So this is the synthetic division. Okay, ready? Here is the algorithm for synthetic division. We already know the answer, right? We have to get the same answer. Here's a question before we start. When I divide degree 5 by degree 1, the result must have what degree? For sure, always, forever. 4. So we expect degree 4. So result or quotient must have degree 4. Is that clear? The polynomial at the top has degree 5. The polynomial at the bottom has degree 1. The answer must be degree 4. Agreed? Perfect. So the algorithm requires us to copy the first coefficient. Always we copy it. Then here's how we proceed. 3 times 1.
3.
We write it above the line under 4 and perform the operations we see. 7. 3 times 7. We write it above the line under 0. Perform the operations we see. We get 21. 3 times 21. We write it above the line like before, and we repeat till the end. And we perform the operations. 3 times 60, 180. We write it above the line, perform the operations. We add 182. And 3 times 182 was, what is it, 546. So I box in 549. Can anyone give us the answer? Remember, we wrote it has to be degree 4. The coefficient is 1 for which degree? X to the 4th plus 7x to the 3rd plus 549 over x minus 3. And this is the synthetic division.
Can you explain one more time why it has to be at the 4th degree?
So when I divide degree 5 by degree 1st, I get x to the 4th. Copy the base, subtract the exponents. From 5, I subtract 1 to get degree 4. Is that clear? Is that clear? Yes? Perfect. Okay. Of course, there is a type 3, which is only long division. Because, for example, for problems like let's look at 15. 18x to the 4th plus 9x cubed plus 3x squared divided by 3x squared plus 1. We cannot use synthetic division. Can anyone explain why we cannot use synthetic division on this example? Because the denominator is not a linear factor. It has degree 2. I cannot use synthetic division if the degree is 2. So in this case, both are in descending order. No missing terms. There are, but at the end, so I don't have to worry about the end. degree 4, degree 3, degree 2, and 2 are missing, but they're at the end. I'm fine. So there is nothing else but the long division for this. So let's start the algorithm. 18x to the 4th plus 9x cubed plus 3x squared. And yes, I can have 2 zeros in there, but there is no point because they're at the end. I don't have to worry about them. So the first question is 3x squared times what is 18x to the 4th? And the answer is 9x. Oh, of course. Yes, I'm thinking of 27. Thank you for keeping me on track. Indeed, 6x squared, of course. So I get 18x to the 4th, but I subtract. Then I get positive 6x squared, but I have to subtract, and I have to write it under like term. Be very careful. You cannot write it under x to the 3rd. Because they are not like terms. Perfect. So then 9x cubed is the next in line, and minus 3x squared. Next question. 3x squared times what is 9x cubed?
3x.
And positive 3x indeed. If I start with x squared, the next one has to be lower degree for sure. 3x times 3x cubed squared is 9x cubed. I subtract. And then 3x times 1 is positive 3x. I cannot write it under this, so it has to be negative 3x outside. But that's okay. It's the next in line. I bring down negative 3x squared and minus 3x. Final question. How do I know it's final? Because this is degree 2 and this is degree 2. I'm done. I have degree 2. I have degree 1. The last one has to be a free term. I know it's the last step. So 3x squared times what is negative 3x squared?
Negative.
Excellent. Perfect. So negative 1 times 3x squared is negative 3x squared, but I have to change. And negative 1 times 1 is negative 1. I have to change, but I have to put it outside. I cannot write it under negative 3x. So negative 3x plus 1, and this is what I box in. I can continue because now the degree is smaller than the degree of the divisor. But the question is, how do I write the final answer? Can anyone give us the quotient?
Right, the entire.
Exactly. 6x squared plus 3x minus 1. Now, this starts with a negative. It doesn't matter if you want to put minus in front, you can put, but let's copy it as plus first. The top is negative 3x plus 1, which is the remainder, and the divisor is 3x squared plus 1. We cannot apply synthetic division here, so if you'd like to check, you will multiply this by this and add negative 3x plus 1 to recover the top. One thing I would like to mention here, if I divide 9 by 3, what is the remainder? Right, the remainder is 0. Why? Since 3 is a of 9. Thank you. What if I divide x squared minus 1 by x plus 1? And I don't care about the quotient, but I know the remainder is 0. What will you say about x plus 1? Factor of, that's it. Please remember that. Always when the remainder is 0, that what we divided by is a factor of the top. Good. So now we're ready to look at rational functions. Your book does not divide or call them the way I like to call them. It doesn't matter. You don't have to call them in any way. But I prefer giving them a name just because when we refer to one type or another, then we know what we're talking about. So 3.5, rational functions. So now let me say this. We started a long time ago with linear functions, the simplest possible polynomial. Then we moved up and we looked at quadratic. Then we moved even higher to degree 5, degree 3, degree 2, degree 3, 5, 4, 6, 7, whatever, higher degree polynomial functions, right? So this was more sophisticated. Well, this one is even more difficult. And after this, in chapter 4, we will introduce 2 more functions and then no more functions. Promise. Done. But this is, I would say, the most complex because it has things that we have not seen before. It has some properties that no other function has from the ones we studied so far. Okay. We also looked at radical functions and the absolute value function. But this one, I think, would be the most involving one. There are many, many, many types of rational functions. I'm only going to discuss 3 types. We can discuss other types, but we are tied to the calculator. So there is no point, really. Type 1, type 2, type 3. And I claim that the examples I'm going to pick are all 3 different ones. So here's an example. Let's say f of x, negative 2x plus 10 divided by x plus 3. Here's another type. Let's say x divided by x squared minus 4. And here's type 3, which is, let's say, x squared minus 1 divided by x plus 3. I claim that they are all different. Can anyone other than Charisse tell us why do I think that? Why do you agree with me or you disagree with me? I claim that they are all different. The sun was in the way today, so I had my tent up. Why? Why do you think, if you agree with me, I claim that they are all different? Do we notice anything? Just compare this to this and to this and say, oh, I think the first one has perfect. Yes, that's what it is. So same degree over same degree. That's it. It can be degree 1 over degree 1. It can be degree 2 over degree 2. It can be degree 5 over degree 5. As long as both degrees are the same, that is type 1. Okay, what do you think about the second one? Anyone else but Ella? Anyone? Can anyone say anything? But higher in the denominator. That's the point. Okay. Degree higher in the denominator. Good. I don't care by how much higher. By 1, by 5, by 10,000. Okay, what about the last one? But this one is specifically higher by 1. Not by 2, 3, 5, or anything like that. I will say degree n plus 1 and degree n. Specifically by 1 at the top. This is why I refreshed your memory on the long division, on this one. However, if you would like me to show you an example, I'll be very happy. If you see an example, if you come across an example in my math lab, I will show it in class for everyone. But I will not put an example like this on the test or final exam. We don't have applications in this book, so this will be dealt with in Math 230. Actually, I just did that with my calculus class. Okay, so at the end of the day today, you'll tell me whether you want to see an example like this. If not, that's fine. And we will look at the first 2. So let's start with number 1. So let's say f of x equals negative 2x plus 10 divided by x plus 3. The question here is graph it. And you can say, why do we always graph this by hand first, or any function that you want to talk about and you want to show us examples in real life situations? Why do we need to graph it first? Because only when we graph it step by step, we understand what the function is all about. Okay? And like always, remember the first example, it will take like forever, and example 2 and 3 will take 3 minutes or less. Okay, so bear with me. I'm asked to graph a function. What is my first thought no matter what? Thank you. Number one must be domain, always. Good. So let's look at this function. We've seen them before. We dealt with them in chapter 1. We did not look at them as functions, but we looked at them as rational functions, rational expressions, or rational equations. So, can anyone give us a domain of this function? Yes, exactly. X plus 3 cannot be 0. Of course, not negative 3. So then the domain is exactly negative infinity to negative 3 union negative 3 to infinity. Awesome. Please, let's start getting a chart going that will help us graph the function. 0 must be in the chart no matter what. And negative 3, and this is what I would like to write. You write whatever you want. You make up your own table. You summarize the information the way you like. I'm fine. I recommend this method. But if you find something else that works for you, use it. But summarize the information. Let me show you, which I don't agree with. Let me just get to that page. Okay, here's what the book does. I'm just looking for an example in this book. Okay. Okay, so they say, step 1, step 2, step 3, step 4, step 5, step 6, 7. And they come up with a graph. But they don't summarize anything. How can I come up with a graph without putting everything that I know together or that I found about the function? So we're going to summarize the information in a table. The same table we used for polynomials. Nothing different. Nothing different here. Okay. Here's the first note. Note number 1. A rational function has a vertical asymptote where it is undefined. There is an exception. I'll put in parentheses, except when the factor goes away. Simplifies, I should mention, better. So if I have x minus 2, x plus 1 over x minus 2 times x minus 3, this factor goes away. X equals 2 is not a vertical asymptote. That's the exception. But in our case, x plus 3 does not simplify with the factor. Yes?
I'm sorry, what is that word?
Yes. So I have not explained what it is. I only wanted to write the note first. So when a rational function is undefined, in this case it's undefined at negative 3, there is a vertical asymptote. A vertical asymptote x equals negative 3 that the function cannot cross because the function does not exist at negative 3. So because it's undefined at negative 3, the function can do this. The sides of around negative 3 to go to infinity. So x equals negative 3 is the vertical asymptote. And the sides go both to a positive infinity. One option. The sides go both to negative infinity. Second option. And the sides, of course, can be positive, negative. 4 different options. So whenever a rational function is undefined at an x value or values, you can have more than one vertical asymptote. The function has a vertical asymptote, has a line that it will never cross, and the function values will go to infinity or negative infinity in four different ways. Now, here's the exception. So I don't want you to think that if a function is undefined, we'll always have a vertical asymptote. Not always. If the factor goes away, that's not a vertical asymptote. The factor that stays will create a vertical asymptote. But the factor that goes away will be a hole in the graph. Okay. So then I will write myself a note right here at the table, with the table. -3 is a VA, vertical asymptote. Vertical asymptote, PTOTE, asymptote. Okay. Knowing that, I will immediately, that's my next step. So first step, I just want to number everything. So in first step, we determine that the domain, and we put it in the table. In step number two, x equals -3 is a VA. I will put myself a note just one more time for you to remember. The factor of x plus 3 does not simplify. In step number 3, I must find the behavior of f of x near the vertical asymptote. What does that mean? One of the four options. Positive infinity to positive infinity, negative infinity to negative infinity, or this. How do I find that? Very easy. I go back to the table and plug in a number from the left and a number from the right. Notice that I don't put those numbers in the table. I don't care for those numbers. I would use those numbers only to determine the sign. What sign? We're here. So I consider that -3.1 and -2.9 are close enough to -3. So I plug in -3.1 in the function. I don't calculate anything. I just need the sign. -3.1 times -2 is positive number, plus 10 is a positive number. -3.1 plus 3 is negative. Positive over negative, I found the sign. Negative. With -2.9, -2.9 times -2 is positive, plus 10 is positive, but -2.9 plus 3 will be positive, right? -2.9 plus 3, positive. Positive over positive, that's all I care about. So the function on the left-hand side of the asymptote will go to negative infinity. On the right-hand side of the asymptote will go to positive infinity. That's how we are going to graph when we get there. Okay, bear with me. When we put everything together and we go to the second example, you'll say, oh, okay. Okay, step number 4, x-intercepts. Of course, and they're multiplicities. If, and multiplicities. Okay, so let's look at the function. -2x plus 10 over x plus 3. When is this function 0, right? I have to write y equals 0. -2x plus 10 divided by x plus 3 is 0. When is a fraction 0? Only when the numerator is 0. Good. So -2x plus 10 equals 0. -2x equals -10. X equals 5. So I'll go back to my table and put 5, 0 in the table, in the correct place. Number 5, Y-intercept. How do I find the Y-intercept for any function? Excellent. F of 0, let's do this together. 0 here, 0 here. I have 10/3, so I'll say 10/3. I'll put it in the table in the correct spot. 10 divided by 3. We're almost ready to graph. So item number 6. Of course, our best friend and behavior. And horizontal asymptote. Okay, what does that mean? We have not seen this before. So let me refresh our memory on every function that we looked at so far in polynomial functions. What was the end behavior? Either negative infinity to positive infinity, or positive infinity to negative infinity, or positive infinity to positive infinity, or negative infinity to negative infinity. Well, type 1 and type 2 are very special. They have a horizontal asymptote, meaning the function at infinities is not going to be positive or negative infinity, but it will approach a number. And for type 1, let's write the next note. Type 1 has a horizontal asymptote given by y equals leading coefficient over the leading coefficient. And this is only for type 1, not for type 2. And type 3 doesn't even have a horizontal asymptote. Yes?
That would be negative 10/3.
0, 0, 10/3.
So we're not solving.
F of 0, I replace
Oh,
x.
it's +3.
Yeah.
I see what, okay.
That's okay. So can anyone give us the leading coefficient of the top? Bless you. Can anyone give us the leading coefficient of the bottom? Remember, they have to be in a descending order, otherwise we will not be able to identify correctly. 1. How much is negative 2/1? Negative 2. So in our case, y equals negative 2 is the horizontal asymptote and behavior. Negative 2. Negative 2. I write myself a note. Y equals negative 2, horizontal asymptote. And I know you're going to say, oh, this is gibberish. What does this mean? Okay, here it is. We haven't even graphed it, but let me explain the table. Because all the information is in the table. I don't care about looking at anywhere else. Okay. From negative 2, function approaches the vertical asymptote going to negative infinity. On the other side, it's coming from positive infinity. It crosses the y-axis, it crosses the x-axis, and approaches negative 2. One more time. From negative 2 down to negative infinity. From positive infinity, crossing the y-axis at 10/3, crossing the x-axis at 5, and going to negative 2. Next note before we graph it. When functions have asymptotes, we have to graph the asymptotes first. So graph the asymptotes first. How many asymptotes does this function have? How many do I have to graph? This function has 2 asymptotes. 1 at -3, which is a vertical line, dashed. This is not part of the graph. It's not a solid line. And the other one, which is y equals -2, which is a horizontal line, y equals -2. I will plot the points I have. Well, I only have 10/3, which is a little bit more than 3. And I have 5, 0. 1, 2, 3, 4, 5. So now let's put this together one more time. From -2 down to -infinity. From -2 down to -infinity. That's the first piece. From -2 down to -infinity. On the other side, from positive infinity, crossing, going to -2. It's a smooth, continuous function. My graph is not perfect. Sorry about that. So this is f of x equals -2x plus 10 over x plus 3. With the graphing calculator, please. Do not forget